a matrix, okay? And the goal is that in the output matrix, a lot of the values go to 0. Okay, so then when a lot of values go to 0, now we've got a pattern, and now we can compress it. Okay, so that's the heart of JPEG right there, is that we're going to apply this discrete cosine transform, and in the output, many times, more times than not, we're going to get a matrix that has a few values and the rest are all zeros. Now that's not true for all matrices, and that's also going to depend on the quality factor, which we'll talk about briefly. So then, as it says, the results are quantized according to the desired quality. Okay, when you have a low quality JPEG, you use a larger value in the quantization table, and so you're dividing by a larger number, and so you result in more zeros, but less detail. So I don't know, how many of you have seen low quality JPEGs? They're kind of fuzzy. You might see the blockiness. So, okay, at least one person. And then, of course, high quality JPEGs look really good. But then they take more space. So the higher the quality, the less the compression. It's kind of a trade-off. So then once it quantizes it based on the desired quality value, they run length encode it. As I mentioned, there's a lot of zeros. So instead of transmitting 50 zeros, we'll transmit 1 0 and say the count 50. Or actually, since we know it's a 0, because 0 is the only number that's going to appear like this, we don't even have to transmit the 0. We can just put in there and code a 50. So now we've taken a few pixel values, 8 by 8 pixels, and turn it into a few values, and then with 50 zeros, and then you take that and apply a WinZip type compression to it. Huffman coding is typically used. Arithmetic coding is sometimes used. And then that's how you end up with this very good compression ratio. So the restored image is very similar when you look at it, but mathematically completely different. Now, this says transform technique number 2. Since I was concerned about time, I hid a couple slides that were transform technique number 1. If you download the presentation itself, they're in there. And there's other techniques too. If you look up hiding in JPEGs, you'll find a number of papers on that. But I kind of like this technique, and I adapted it for my class. It's an adaptive discrete cosine transform least significant bit technique. But rather than hiding in the least significant bit of the pixels, it hides in the least significant bit of the discrete cosine transform coefficients. And it's adaptive. All right, so first it does this capacity estimation. Okay, it says how much can I hide in these particular discrete cosine transform coefficients. And it uses both the quantization table and the coefficients themselves. So basically it takes a log base 2 on the quantization table and gets a number. Okay, and then it takes a log base 2 of the discrete cosine transform, the magnitude of it, since you can't take a log of a negative number, it just gets the magnitude. And says how many can I hide in there? What's that value? And takes the lower of the 2. Okay, so it's kind of based on both the quantization table and the actual discrete cosine transform values. Here on the screen now is just some of the symbols. Q is the quantization table, C is the ultimate capacity, M is the max number of bits, D is the DCT coefficient, and E is the number of bits that can be embedded. And so we'll see that a little better here. All right, so here we have a table, and this is a quantization table. Okay, and I just arbitrarily picked X and Y direction here. And so we take the log, for each individual element of this table, we take the log base 2 of that. And we can also factor it with an alpha value, which we'll see. You can pick alpha. In experimentation, I've gotten alpha up to about 4. And once I go higher than 4, perception starts to be easy. Okay, so I generally keep it between 2 and 4 to scale the quantization table by. And then we get the log base 2 of the DCT coefficient itself, the corresponding one. So if we get the log base 2 of 16, that's going to be a 4. And then we get the log base 2 of the corresponding DCT value, which is the smallest one. That's how many bits we can hide. So then we substitute our message bits into the bits of the DCT coefficient. So in this example here, let's say that I use this quantization table value of 11, which is right there. Take the log base 2 of that, take the floor, round it off, or not round it, but just take the floor, and that gives you a 3. 2 to the 3rd is 8, 2 to the 4th is 16. If the corresponding DCT coefficient happens to be a 70, I take the log base 2 of that, I get 6. Well, 3 is less than 6, so I can hide 3 bits in there. And so I take my message bits and replace the lower 3 bits of this 70 with the 3 bits of my message. And I do that for every one of these. Okay. Now in a low quality JPEG, most of these down here in the lower right hand corner are going to be 0 anyway. And I can't hide in 0. Log of 0 is undefined. And so of course in the program you want to avoid doing that or else it crashes and so forth. You can't hide with just 1. If it's a 1, it might go to 0 and then it gets encoded differently. So you need it to be at least a 2 to even hide there. So low quality JPEG, you're going to have a few coefficients to hide in. High quality JPEG, you're going to have a lot more of these coefficients to hide in, and you'll see kind of the capacity of the high quality versus the low quality shortly. And so it does that for each 8x8 block and then for each color plane. Okay. A few other things. This author had a block classification technique where he said, let's measure the complexity of this block, and if it's higher complexity, then we can hide a little bit more, so it tweaks the values a little bit. If it's lower complexity, then we can't. And so basically divided the blocks into 2 classes, either uniform or non-uniform. And if it was a non-uniform block, we could assign a little bit larger alpha value. Okay. Now, here we got that problem again. If we go and change the value of the actual DCT coefficients, when I come back to measure the uniformity later, now it may not come out the same. It may not meet that threshold. Okay. So in my implementation of this paper's algorithm, what I did was I just used the upper 4 bits for uniformity measurement, and I limited my hiding to the lower 4 bits. So I lose a little bit of capacity, but then I don't have any problems with which block is uniform and not uniform because I don't alter the upper 4 bits. So my calculation during embedding is the same as during extraction. But that's what this formula is here. The G, that's the threshold. Sorry, that's the calculation, and then you meet some threshold, which the paper doesn't tell you. So you just have to experiment with that. But you add up all the DCT coefficients from 1 to 63. You leave out the 0 coefficient. That's usually the largest, and so they left that out of the measurement there. And take the square root. That's just a kind of a root mean square technique. And then you see if it's above a threshold, it's uniform. If it's below a threshold, it's not uniform. That type of thing. Well, I mentioned this already. Now, the author with this problem, the way he solved it was to modify the quantization table and set the last byte value in the quantization table to a 1. Well, that's great, except of course that's a very easy detectable signature, right? You find a 1 in there, you just look in the quantization table, find the 1, and say, hey, this has got something wrong with it, because usually that wouldn't happen. Okay, so I did the solution as I mentioned already. All right, so here's the original. Anybody been there before? Joel, all right. Nobody else, at least nobody that wants to admit it, right? Yeah, I was there, but I don't want to tell anybody. All right.
It stays
there. Yeah, it stays there. All right, so there's the original. And here's with a quality of 90. Okay. Now, I found through experimentation with this program that low-quality JPEGs don't work too well for hiding. I can't hide very much without it being noticed, and we'll see that. So I set this one at quality. And I set alpha equals 1, and I set the uniformity factor to 1. That's what the A and the U are. And I hid with about 1% capacity. So there's really not much change to detect. Now, what about this one? Can you tell there's something weird about it? This one I bumped alpha up to 4 and U up to 4. And I got close to a 20% capacity, which is pretty good. If you have a 3 megabyte JPEG, well, let's make the math easy. If you have a 4 megabyte JPEG, then 20% capacity is what, about 800K. That's a pretty reasonable capacity with that. And you can't really see it. Can't really tell. If you were to compare this image to the original, you could probably notice some slight variations in some of the pixels. But if you just had those two and I said which one has the data hidden, one or the other, but you can't really pick out which one. You don't know which one is right and which one is wrong. All right, let's look at 50% quality. Here's the original 50% quality. Looks pretty good, right? Does it look pretty good there? Okay. Now here's with alpha is 1 and U is 1. Can you see anything there? Can you see a difference? I can on the monitor. I can see at least on this monitor, I can see the sky kind of less uniform. See the sky kind of little bands in the sky a bit. Okay. And then with alpha equals 4 and U equals 4.